All right, so let's tie everything back into confidence intervals. All right. What we've been doing is very similar to confidence intervals. So remember, confidence intervals are just an interval estimate for the population. We get a sample and we can estimate that the population with certain level of confidence is within some interval. And so instead of doing a hypothesis test, we could do something very similar. We could take our p hat and make a 95% confidence interval with p hat. This is the same, well, very, very similar to conducting a two-tailed test at a 5% significance level. 95% inside, 5% outside. All right. So that, remember, confidence interval, 95% means there's a 95% chance that the true population proportion is in the interval. So if the proportion from that null hypothesis, that P naught, is in the interval, then we'll say, there's not enough evidence to doubt. We'll fail to reject the null. If, I don't know why I'm keeping my hands up like this, if the proportion's outside that interval, then we say, okay, there's a 95% chance that if that proportion were true, it'd be in the interval. So we have cause to doubt. All right. We have statistical evidence to say, all right, it's no good. And that's another way of approaching these problems. So let's look at an example. The CDC in 2008 reported that 34% of adults in the US are obese. And a county health service planning a new awareness ran a random sample of 750 adults, and 228 were found to be obese. P hat going to be 228 divided by 750 in our little sample. P naught, right? That assumption, if we were doing hypothesis testing, would be 34%. And do these responses provide strong evidence that the 34% is not accurate? So again, we could do a hypothesis test, but let's use a confidence interval. Construct a 95% confidence interval for the proportion of obese adults. So our confidence interval is going to be centered at our sample, plus or minus z star, our critical z-score, times the standard deviation for that sampling distribution. It would be a good idea to check that we can use the sampling distribution with the central limit theorem, but we're going to skip that here. P hat, Q hat over N. Confidence interval, P hat is 228 over 750. What is that? It's 0.304. So again, our sample has lower obesity levels than the CDC's numbers. The question is this statistically significant to show that this region is different? This is going to be 0.304. What's a critical z-score for 95% confidence? I believe it's 1.96. This means 1.96 standard deviations above the mean and below the mean contain 95%, the middle 95%, times the square root of p hat, 0.304, times q hat, 0.696, divided by n, which is 750. And you type this all out and you're going to get our interval. The minus is going to be on the left. Calculate that real quick. 0.304 minus 1.96 times the square root of 0.304 times 0.696 divided by n, which was n 400? No, it was 750. All right, so the lower bound of our confidence interval is about 0.2711. So we're 95% confident that the obesity levels are going to be between 27% and 33.69%. All right, this is our confidence interval. If the proportion from the null hypothesis is outside the interval, we reject the null. So we're 95% confident that this true proportion of obesity in this region is in this interval. So we're 95% confident that that this 34% number is not right. Right? 0.34 is outside this interval. So we reject the claim for this region. It's kind of like if we were doing a hypothesis test and we found a small p-value. All right, so we found our confidence interval, and oh, we should interpret, right? It says, how does this relate to the confidence interval? We are 95% sure that the true p, the population proportion, is in the interval 27% to 33.69%. So with a significance level alpha, we reject the null hypothesis. That's another way of phrasing this answer, and a connection between confidence intervals and hypothesis testing. And that's this unit. Let me know if you have any questions, and good luck.